Hello everybody, in today's video we're going to talk about current density and drift velocity. So now we're going to start talking about drift velocity. Drift velocity is the speed drift through a conductor. For example, let's say we have a metal wire right here that's filled with electrons, and we're going to see that these electrons, their drift velocity is very slow. But the reason you notice that they're really fast is because these electrons, they are incompressible and they act somewhat like a fluid. So when you apply a negative and a positive difference on each side, causing an electric field to push them down one way, it's almost instantaneous. This is what's called the signal velocity, or the signal speed. And this is 1/3 of the speed of light, so it's just 10 to the third power of meters per second. This is what you notice immediately when you power on a device. But these electrons actually drift very, very slowly. Like sometimes, if you have like a 10 millimeter like wire, you might see something like 10 to the meters per second of speed. And note that this drift velocity is dependent on the material, how wide it is, and like how much current like per second you're gonna get from this. So this is not dependent on the material working with. And another thing to add to this is electrons, they kind of just bounce around. So we're gonna get green right here. As these bounce around and hit the walls and drift kind of like towards where they're gonna go, they do lose some energy, which is kind of where we get thermal energy and also light. So when you make these wires thinner, you actually increase the amount of times they bounce, and it produces light. This is what you see in forensic light bulbs. And we can find drift velocity from our current equation. So current through this cross-sectional area is equal to the drift velocity times the density of the electrons. So this is going to be E over meter squared. And then it's going to be times the charge of electron, and it's also going to be times the area of the cross-sectional area that we're passing through. As you can see, it's kind of like a circle. We'll just draw it right here. This is equal to pi r squared. Really good to remember. For whatever reason, if you can't remember certain shapes, the areas, if you just take the center right here and you go from here, you can get the circumference is equal to 2 pi r. But if you take the antiderivative, that gets you the area. And if you take that again, you also get to the volume. But this is a 2D object, so there might not be much to find here. And that's better with spheres. Now we're gonna get into current density. Current density is very useful when calculating the velocity, as if we remember it, our current is just a scalar quantity of the change of charges over a cross-sectional area per time. And charge density, which is just equal, we're going to use our symbol of, and charge density, which we're going to use J, is equal to our current divided by the area of this cross-sectional area that we're looking at. So this will have a vector associated with it. So we'll draw like our area vector, and then we'll have our current density that is passing through here. This can be useful for finding our drift velocity, as mentioned before. Now we're going to go into a practice problem where we can kind of like better explain this idea. And there's one more idea I want to talk to you about when it comes to current density. If we create a new page right here, our current from before, we can get our current back if we integrate over the area of our charge density from before with the dot product of our area. This will get us back to our current density, which is just units of charge over a time. And we know this is going to be something like our current over the velocity times some type of area, and this will get us back to our current from before. This is a very good equation whenever our charge density kind of varies as it passes through some type of wire, which happens often. Now let's get into our practice problem where we can apply this idea. Now let's consider an aluminum wire that has a cross-sectional area of 33 meters. So when I solve problems on practice problems or exams, it's always good to write down the variables. Even though you're reading them, just the act of writing them kind of gets it down in your head, like what you're working with. So consider aluminum wire with the cross-sectional area radius of 33 meters. So notice cross-sectional area. This kind of that tells us what's going to be for our area that our electrons are going to be passing through. It's also a kind of a hint if you're a little bit lost, as this will ring a bell in your head. The magnitude of the current density has been modeled as J is equal to C of R squared. This is going to be the equation we're going to be working with for integral to keep things a little bit cleaner. And we know that the constant is equal to 5 times 10 to the 6th of the amps over meters to the power of 4. Now, what is the current through the intersection of this wire at little r, which is just half of our previous r squared? So this is going to be a little bit interesting. So instead of like, what is the current through the whole thing, we want to know the current through half of it. So this is going to look something like this. And let's kind of like draw our wire too, because this is a cylindrical wire that our electrons are going to be passing through. We'll have some red electrons going through here, and we want to go back to our integral, because if we recall, we can get our current from a varying current density from before if we just take the integral of our current density with our dot product with our area, or dA. Note that our d of a, we're integrating over a circle, so we're going to use radiant coordinates, which d of a is going to equal r of dr and d theta. And the reason we have this r here is because these are like pi cuts like of a circle, and r is just our variable that comes with it as we go over dr d theta around the circle. So that's going to be what we're going to put in our integral as we solve through this problem. So we know that our integral is going to be from 0 to 2 pi because it's a complete circle. And then our first integral is going to be from 0 to r because that's how far it's going to go out instead of capital R. And then we know our J, which is our current density, is equal to C, which is our constant, times r squared times r again, and then we have our dr d theta as from before. So we can easily get the 2 pi. This is a simple integration since we don't have any varying angles. And then notice that we're going to get r cubed up here, which is going to leave us with 1 over 4 r to the power of 4, and it's going to be from 0 to r, so we're just going to get lowercase r in this case. And then this whole thing looks right, I think so, right? And that's what we just integrated to get. Now we notice we need to substitute our little r with our capital R, because that's what we're going to be going over. But we don't know, I guess we do know little r. It's just 1.5 millimeters, but pretend we don't. And we're just going to substitute it for 0.5 times 3 millimeters. Just kind of go with the flow here a little bit. So we know that this is going to equal to 1 over 4. And then we're going to get like 1 over 2 r, and this is going to be to the power of 4. Okay, so we know that 2 to the power of 4, which we're going to write out here, is equal to 16. And then if we times that to 4, that's going to give us 64. But 64 divided by 2 gets us back to 32. So this is going to be our fraction as our constant here. So we're going to start with 1 over 32 pi. And then we're going to have some r to the power of 4. And that should be all of our variables. Yep, and now this is what's equal to our current from before. Now we just need to substitute our radius, and this will kind of give us what we need to know. And remember, this little r should be represented with the capital R as we substituted it back out. So because we know what big R is, we might not know what little r is all the time. So that's what we're going to stick with. And now let's substitute in the variables. So 1 over 32 times pi to the power of, we're going to say 3 times 10 to the negative 3 meters. And also don't forget your constant. So this is something we kind of left out as it's easy to kind of like miss it. But we had a constant outside our c, which we took out of our integral from earlier. Now this is where our constant comes back in, our constant c. So this is going to equal to what we were provided up above. C is equal to 5 times 10 to the power 6 amps over meters to the power 4. And notice how these meters cancel out. And that will just leave us with the current in amps. Now take a moment to put this into your calculator, and then I'll give you the answer to see if you got it right. Alright, now that we're here, the answer should be 3.98 times 10 to the negative 5 amps. So we're just going to represent it with a capital A. So that answers the first part of our question. Now the problem asks us, what is the drift velocity given that the aluminum free charge per volume is equal to that variable up there? So that's a really good question. We're going to start by re-erasing some of our work here to give us some room to work in. So we know what our current is, which is like the main component. Now let's calculate the drift velocity, like how fast are these electrons passing through our wire. We already know that the area is very small, so these can be moving pretty slow, as we'll see in a moment here. So how do we find drift velocity? We know that the current is equal to Q over T, dt dq, but it's also equal to, as we're going to see here, it's equal to, let's draw a circle to kind of give us an idea. So imagine you have these electrons passing through. There's going to be some density of them per volume going through at a certain point. And then we're going to have their charge, which is just the charge of a single electron. And then we're going to have the velocity of their drifting through this cross-sectional area. And then that leaves us with our cross-sectional area, which is equal to pi r squared. And as we'll see here, we know all these variables now. We know n, we know q, we know our area because we know the radius, and now we also know the current. So now we can just rearrange these to solve for our v of drift velocity, which is equal to current divided by our free charge density times q times our area. And that's just going to leave us here with what we need to calculate. So let's put in these variables. So this is our amperage, and then our free charges that were just provided. Free charge density is 1.8 times 10 to the 29th coulombs per meter squared. And then we got our electron charge, which is 1.602 times 10 to the negative 19th power This is a really good variable to remember, as you're going to be expected to in physics for B. And then let's just erase this so we can make our equation look a little bit nicer. And then our last one's going to be area, which is pi times our radius from before, which is going to be, we're just going to put 1.5 meters times 10 to the negative 3 here, don't mind this here, and this is going to be squared from before. And now calculate this and see what you get. Alright, now that we calculated it, this is the answer I got. So I got 4.88 times 10 to the negative 11th meters per second. So as we can see, this is very, very slow. And the reason why this happens is because our current is also very slow, and our cross-sectional area is also very small, and our density is associated with the material, so that's a constant to aluminum, and so is charge. So the only things it can change is the cross-sectional area and the amperage, which both of them are very small, and this is why we got them moving so slow, which is, it's crazy to think electrons move that slow. And thank you for watching my video today. I appreciate you watching to the end, and have a good day.